Muchísimas gracias a nuestro speaker invitado, un honor haber compartido con él y que nos haya dado toda su visión. Seguimos con este Foro Nacional sobre Inteligencia Artificial en Salud, organizado por ULACIT y la Cámara Costarricense de la Salud y DIGIT. Para cerrar esta primera parte de nuestra jornada, tendremos la ponencia titulada Voz, Signos Vitales y Algoritmos Predictivos, una nueva era en la detección temprana. Me complace darle la bienvenida a nuestro conferencista invitado, el señor Nguyen, director ejecutivo en Predicate. El señor Morris solo habla inglés, así que igual le damos un caluroso aplauso.
Thank you. Buenos días. My Spanish is not great, so I apologize. I'm the second person today that will be speaking to you in English. I do apologize about that. Maybe next time I'll come back and speak in Spanish. Thank you for the invitation to speak today. I'm Morris Nguyen, the founder and CEO of Predicate. I'm happy to share some of the research and development work that we're doing with natural language processing and building a predictive model for sepsis. We know that sepsis affects approximately 50 million people around the world every single year and is responsible for 1 in 5 deaths. With sepsis, time is of the essence. It's important that the diagnosis is made quickly so that treatment can start very promptly. Every hour that treatment is delayed with sepsis increases the odds of mortality by 7.6% per hour. But sepsis is also very difficult to detect in the early symptoms. The symptoms present very vaguely. Patients can come in presenting with fever, fatigue, malaise, feeling just off. And it's difficult for physicians to be able to make that diagnosis. The idea is, can we detect sepsis as early as possible? Because every hour that you delay increases the chances of mortality. And you can see there that mortality increases as you go closer to organ dysfunction. So we asked the question is, can we detect, not only listen to what patients are saying, but detect subtle patterns in the speech, in what they're saying, understanding key words and phrases from when they report their symptoms, and using artificial intelligence to interpret those signals and those patterns within the speech. The current challenge today is emergency departments all over the world are fast-paced. They're often faced with very labor shortages, workflow challenges, fragmentation of data, and they cannot spend enough adequate time to detect sepsis early, especially in the early stages. The workflows are very constrained and very difficult and inconsistent. And the rule-based algorithms that are running on the systems today, so think about your EHR if you're using one. There are rule-based alerts that come up. The problem with that is these rule-based systems based on QSOFA or SIRS criteria lack the temporal context to really detect sepsis at the early stages. And it's also based on retrospective data, not prospective data or real-time data. There's strong scientific evidence, published scientific evidence behind the use of artificial intelligence to predict for sepsis. Here's one example. This is the Brandt et al. 2024 study. And what they did is they applied natural language processing to nursing triage notes in the emergency department. Over 1 million patients were looked at. And what you can see there is that you can see that this line here represents the use of natural language processing in the unstructured text in the clinical notes to predict for sepsis. And the AUC is right here at 0.94. So high specificity, high sensitivity to predict for sepsis. When they added in the lab data as well, that AUC increased to 0.97, which indicates that there is value in detecting words in the clinical notes to predict for something like sepsis. Then in Zhang et al. 2021, they did a time series model looking at can you predict sepsis 4 hours before the onset of sepsis, which is difficult to do. But you can see the current method. This is what we're used to seeing today clinically. QSOFA, SIRS, NEWS, MUSE, that the average area under the curve is very low, 0.6, 0.5, not very good. But when you apply machine learning models, that area under the curve increases to above 0.8, which is where we want to be. So again, more evidence that supports that machine learning models can predict for sepsis better than current methodologies. And lastly, the Florin et al. Study was a systematic review of 130 models. And what they found was that if you look at the x-axis here, this is the hours before onset. Ideally, we want to be able to predict for sepsis as far out from time zero as possible. So how good is the model at predicting sepsis the further out from time zero? And you can see that this line here represents decision trees. This is what we're doing today, those role-based algorithms, very low AUC. Then it starts to improve as we use machine learning methods. And the best one here is the neural network, which is what we are using to help build OpenDX. The idea behind our platform, OpenDX, which stands for Open-Ended Diagnostic Reasoning, is we want to combine the use of wearable biosensors. So think about like your sensors you wear to detect heart rate variability, respiratory rate, SpO2, and core body temperature, to combine that with what the patient reports as symptoms. It's a fusion of the two models together, which we call OpenDX. The language data helps to give context to what the wearable data is showing, the physiology, and the physiology helps to quantify what the language data is showing. So when patients typically come in for an OpenDX study, you conduct the triage exam like you normally do. We are not disrupting the clinical workflow at all. These are the usual questions that you would ask patients during a triage exam. The patient will respond. What's happening is that we are recording, we are capturing that raw audio data, we're transcribing it from audio to text, and then we're using transformers to go from text to train our AI model. What we're looking for are certain keywords and phrases that predict for sepsis, that are hidden in the language, because as clinicians, we can miss words, especially in fast-paced environments. We have too many patients coming in. We're busy. We're not going to listen as intently to the patients as they report their symptoms. And also, there's high levels of subjectivity when patients report. Clinicians have implicit bias. So what this is doing is the algorithm is listening for patterns in those keywords and phrases, and then using that to weigh on the contribution of those words to the prediction of sepsis onset. This is one of our studies. This is done at Haspa Escuela in Tegucigalpa, and it's Honduras' largest reference hospital with 1,200 total beds, 119 ED beds, a volume of about 300 patients a day in the emergency department. Very sick patients. They have 3 emergency department physicians and 2 nurses, so very understaffed. And we just finished the study with 270 patients enrolled. We're in the analysis period here. But notice that this is what happens when patients come into the study. When they meet criteria, they're consented, and we put a wearable device on them here. This is a device that collects baseline physiology, heart rate, respiratory rate, core temperature, SpO2, arrhythmia detection. Then the physician talks to the patient, interviews them, using structured interview questions, and everything is recorded. We're interested in knowing what the patient reports as symptoms. This particular patient is a 49-year-old female coming in presenting with tachycardia, fever, unresolved illness for 10 days. She had abdominal pain. She had actually experienced mentation changes, confusion, and everything that could get missed if in this fast-paced environment. So what we're doing is we're using a time series analysis to analyze what she's saying in her interview during the triage exam, combined with what her physiology is showing. Okay, and none of this is relying on, at Hospital Escuela, they use paper charting. They don't use EHR. So the platform is designed to be independent of EHR to get the data we need. There's a lot here, but this is the architecture, essentially, of OpenDX. What I want to point out here is that, there are multiple layers. There's a data ingestion layer here, NLP embedding layer here, and then we have a wearable data. So what's unique about OpenDX, it's a fusion of using the time series wearable data with the NLP layer together, and we extract features from that, and then we use a decision tree method to pull out to predict for sepsis. Okay. We currently have study commitments across 7 countries, 5 continents. It's important when you're building an AI model, especially one that predicts for sepsis. 85% of sepsis occurs in the global south. And we didn't want to simulate a model. We wanted to go actually out to the clinical setting and collect the data from the patients itself. So you can see here, currently we have studies wrapping up in Honduras. We have US studies starting soon. Chile is ongoing. Ghana is ongoing. Ireland is next. And then we have Southeast studies there. Maybe we come to Costa Rica to do studies as well. That would be very good and nice to do. So this is my thoughts on the future of healthcare. It's important that healthcare not only listens, but it understands and it learns. The use of natural language processing as part of an AI-based predictive model can predict not only for sepsis, but other conditions as well. We're looking for things in our pipeline of ischemic heart disease and severe respiratory illnesses, and potentially the next pandemic. All these things are going to be in the future of healthcare. We think that to help augment the clinical decision, it requires not a single dimension of data, like just wearable data or just labs. It requires a fusion of different modes of data. So we're using wearable, labs, and language. And it has to be context aware. The AI model gets smarter. It learns with every patient. And the more detailed data we can provide it, the better it gets. And as OpenDX continues to learn across population and languages, it's very nuanced in care environments, it can be deployed in any setting so that it can help augment that the decision-making from that doctor or nurse. Gracias.